already discussed what are the, what is the problem statement, that we have a circular wire of radius r, and let's say we can also put a length L, and through the wire there is transmission of heat conduction. It's not, sorry, what I'm saying, transmission of electricity, and some electricity or the electrical energy is getting converted into thermal energy, and that thing is resulting in conduction, heat conduction within the wire. So first of all, let us assume that this is direction R and this is Z, and there is QR, heat transfer is happening in the R direction, and the generation is happening at exactly at the middle. T is a function of R, generation is at R equals to 0 at the middle, let's say, assume that. And for this we need to write the governing equation, and then we need to write the problem boundary conditions, and then we can solve it. Again, whenever it comes to governing equation, there are two ways, but I would say at this point of time that the easier way out is the using generalized governing equation. So let us again go back to the cylindrical governing equation here. What I'll do here, one of the term is not added, as you can see. Okay, so this is the cylindrical governing equation. One of the term SC is not here. They have written this equation without its external heat source term. But when we have derived, you can see that we have added a source term, so that it will not be an issue when you are doing a problem. So assuming that the problem is steady state, there is no flow, the problem is incompressible. Of course, there is no flow means no incompressible, compressible really doesn't matter. And there is no viscous dissipation, because there is no flow, there is no velocity, there is no viscous dissipation, and only Q, the flux is active only in the R direction. That means heat transfer is happening only in the R direction, in the outward radial direction. And what else are there? And other direction, of course, heat transfer is 0. Then you can see that the equation will become, this is 0, 0, 0, and 0, not 0, 0, 0, 0, 0, not 0. Okay. So now your equation becomes minus 1 by R dou dou R R Q R plus SC equals to 0. You can also refer the book and see how this thing is derived from the control volume approach. So let me just go back and write down the equation, the governing equation, which is minus 1 by R minus 1 by R dou dou R RQR plus SE here. In this case, the generation rate is SE. I have already discussed before. Equation number 1. Okay. We can also write this equation now as simply DDR RQR plus minus R SE equals to 0. Now boundary conditions. If you look at the boundary condition, the temperature boundary conditions, you can see that okay, one thing I have not mentioned, let's say the ambient temperature is T naught, and here also temperature is T naught. Okay, like there is no difference between the ambient temperature and the surface temperature. So that gives us at R equals to R, temperature is T naught. Another condition is the heat generation is maximum here. Okay, and of course they are minimum along the walls, at the not walls, at the surfaces. So exactly the same way we have done before. At R equals to 0, the gradient, temperature gradient is 0. Okay, because heat generation in maximum here, assuming that it is maximum here and they are minimum here. So here at this middle point at R equals to 0, the gradient will be 0. Now using these boundary conditions, equation number 3, you can solve equation number 2. So you can start with equation number 2. What you can do is you can either substitute QR in terms of Fourier's law of heat conduction, or you can do it later. So if I would like to integrate equation number 2, we will get RQR equals to R square SC divided by 2 plus C1. We can put as equation number 4, and QR looks like R SE by 2 plus C1 by R. Question number 5. Okay. Now if we substitute the governing equation here, Fourier's law of heat conduction here, we will get minus K dt dr equals to R SE by 2 plus C1 by R, or dt dr equals to minus SE by 2K R minus C1 by K 1 by R. So now what you can do is you can obtain an expression for T here in terms of C1 and C2. Once you got expression of T, you can obtain the values of C1 and C2 from equation number 3, and I would like to get the final expression. If you want to see the final expression, please refer the book. Just the knowingly I am not writing the final expression here, so that you do it and go back to the book and check it. Okay, so I'll stop here and I will make sure that you go to the book, get the temperature profile, because now it is all about integration. Find out what is average temperature, find out what is delta T average, find out what is delta T maximum, whatever is mentioned in the book, and try to finish this problem. Okay, and also the previous problem with composite wall. Okay, so I'll stop here this part, and I hope you understood what I have discussed. Please go through this problem, finish it up. There are certain problems in the book as well, but before telling what are the problems in the book, I will give you some time to look into the governing equation, look into the derivation of equation, energy equation, and work out the composite wall problem in Cartesian and cylindrical coordinate system, and this problem with the heat generation inside a electrical wire problem. Try doing this problem, start the problem from the governing generalized governing equation as well as by